Hi everybody! Today we're going to talk about intermolecular forces. So remember that in chemistry, the word force usually means force of attraction or force of repulsion. So we have intramolecular forces and intermolecular forces. So molecular means molecules, obviously, and here we're talking about forces of attraction. And the word intra means within. So these are attractions that are within a molecule, like intramural sports are within a school, and so intramolecular means they're within the molecule. So attractions within the molecule. Another word for intramolecular force is bond. So we usually use bonds as opposed to intramolecular force just because bonds are easier to say. So if we have a a water molecule here, the hydrogen and the oxygen are bonded together. This would be the intramolecular force, the attraction between the hydrogen and the oxygen. So it's within the molecule itself. So ionic, covalent, and metallic bonding, those are the intramolecular forces. The topic for today is actually intermolecular forces, and inter means between, so these are forces of attraction between molecules. That's what we're focusing on. That's what we mean by IMF. And so these are between molecules. If I have a water molecule here and another water molecule here, there is a force of attraction between them. That's why water forms drops. So if it rains and you're driving on your windshields, you'll find little droplets of water. That's because there are strong attractions between the water particles. So these are the intermolecular forces. Between intermolecular forces and bonds, the bonds are way stronger than the intermolecular forces. To overcome these intermolecular forces, you just need a physical change. Like if I take some liquid water and turn it into gaseous water, that is overcoming the intermolecular forces because you're separating those water particles, so you're overcoming that attraction between the water molecules. Versus here, if you were to break these bonds, that would require a chemical change, and it would take it from water to hydrogen and oxygen. So that is very hard to do. You know, at home you can very easily evaporate water, overcome these intermolecular forces, but it's almost impossible to break these bonds and turn them into oxygen and hydrogen. So we are focusing today on these intermolecular forces and how to tell what kind of intermolecular force is in a given substance. So there are actually 4 types of intermolecular forces, and these are also known as van der Waals forces. And the first type of intermolecular forces is called ionic interactions. Ionic interactions. So guess what type of substances it occurs between? Ionic substances. So something like NaCl. So if you look at a formula unit of NaCl here, it's made up of Na pluses and Cl minuses. Another formula unit of NaCl is here, made up of also Na plus and Cl minus. The positive ion of one formula unit is going to be attracted to the negative ion of the other neighboring NaCl formula unit. And so that attraction, that is your ionic interactions. Vice versa, the negative ion of one formula unit is going to be attracted to the positive ion of the other formula unit. So again, these red dotted lines, that shows you the intermolecular forces, which are again the ionic interactions here. Ionic interactions are really strong. They are the strongest of the intermolecular forces, and the reason for that is because these are attractions between a full positive and a full negative charge. And so very strong attractions, and that's why ionic substances have very high melting points. It's very hard to get them to overcome these intermolecular forces and break the crystal and melt and turn from solid to liquid. So 4 types of intermolecular forces. The first one is ionic interactions, and these are by far the strongest. The other 3 types of intermolecular forces occur between covalent substances. And those 3 intermolecular forces are called dipole interactions, hydrogen bonding, and London dispersion. So again, intermolecular forces, there's 4. Ionic interactions are the strongest, and then those 3 are weaker, and those 3 occur between covalent substances. Between those 3, hydrogen bonding is the strongest, followed by dipole, and then London dispersion is very, very, very weak. So for the majority of the questions for this chapter, they are going to be about covalent substances and these three types. So let's see the differences between these three types. We're going to start with dipole interactions. And so the word dipole, di means two, pole means side. So these are two-sided interactions. So they occur in two-sided molecules, which are polar molecules. Remember, polar means sided. So things like HCl, for example. So if you look at an HCl molecule, remember that chlorine is slightly more electronegative than hydrogen, so it gets a slight negative charge. The hydrogen gets a slight positive charge. And so if you look at these where it's blue, that's the chlorine end of it, partially negative. Where it's like an orange color, that is the hydrogen end of the molecule, that is slightly positive. And so the molecules will arrange themselves so that the slightly positive end of one molecule is next to the slightly negative end of the neighboring molecules. And because they're slight positive and negative, there's an attraction right here, and right there, and right there. And so these attractions, those are your intermolecular forces that are called dipole interactions. So all of these are your dipole interactions. They're very similar to the ionic interactions, right? We said it's positive and negative attraction. But these are weaker because these are partial charges compared to in ions you have full charges. So these are weaker than ionic interactions. The next type is hydrogen bonding, and it's very misleading in its name because they're not actual bonds. Remember, they're intermolecular forces. So they are the attractions between the molecules, not within the molecule. So this is not a hydrogen bond. The attraction between the whole water molecule and the other water molecule, that's the hydrogen bond right here, the dotted line. So hydrogen bonding is a special type of dipole. It's just a little bit stronger than dipole. And so because it's a special type of dipole, it also occurs in polar molecules. It's just that it occurs in special polar molecules, in extremely polar molecules. And so it occurs in polar molecules that have an HF, HN, or HO in them, because fluorine, nitrogen, and oxygen are the most electronegative atoms on the periodic table. And so if you look at the electronegativity difference between hydrogen and fluorine, or hydrogen, nitrogen, or oxygen, it's a big difference. And so these molecules are extra polar. They're very polar. So water is an example. And so in water, the oxygen gets a partial negative, the hydrogens get a partial positive because oxygen is more electronegative than hydrogens. And so again, the positive end of one molecule is going to be attracted to the negative end of the other molecule. So same thing as ionic interactions, same thing as dipole. They're all about positive end of one molecule attracted to the negative end of the other molecule. The only difference is the extent of that attraction. And so the partial positives and negatives here are a little bit bigger than the partial positives and negatives in a regular polar molecule. And so these are slightly stronger than a regular dipole because these are strongly polar. But it's again the same exact idea. The last type of intermolecular forces is called London dispersion. London is named after Fritz London, a chemist, not the city of London, and dispersion because it has to do with the movement of electrons, the dispersion of the electrons, the random motion. And these occur in all molecules. Every single molecule has London dispersion forces. However, they're extremely weak, that they're only significant in nonpolar molecules, because if it's a polar molecule, it will have either H bond or dipole, which are way stronger than London dispersion. So what happens is, let's say this is a nonpolar molecule, like let's say Cl2. And so this is another Cl2. And so Cl2 is nonpolar, the electron cloud evenly distributed. But because the electrons in that electron cloud are moving very randomly, very quickly, just by coincidence, because of the random motion, they might be distributed in one area of the molecule more than another. Just for an instant, as they're moving randomly all the time, they might be in one spot more than another, just for an instant as they move. If that happens, then for that instant, that split second, if there's more electrons on this side of the molecule, then this will get an instantaneous dipole. That means just for an instant, it's going to have a slight partial negative charge. And this side will have a slight partial positive charge. When that happens in this molecule, that causes the neighboring molecule to do the same thing, because there's an electron cloud here, and when this electron cloud it's negative, it sees that there's a partial negative here. Those electrons are going to push towards the left side here, and also make a partial negative here and a partial positive here. When that happens, again, for just that instant, now that you have a partial positive and a partial negative, there's an attraction right there. And that is what the London dispersion force is. Extremely, extremely weak because it only happens just for an instant by coincidence due to the random motion of the electrons. Happens for an instant, stops. Happens for an instant, stops, because the electrons are just moving randomly. If you have several molecules and they have London dispersion, to compare between them, usually the molecule that has more electrons has stronger, and is larger in size, has stronger London dispersion. So that's what this is saying here. The more electrons and the larger the molecule, the stronger these dispersion forces. I have a little video for you to watch. Oops. Trying to exit out of here. So the video is about London dispersion forces. Let's see if I can play it for you here.
The movement of electrons around a molecule is to some extent random.
So they're just randomly
This
moving
means
electrons.
that, at a given instant, the electron cloud may be concentrated momentarily at one end of the molecule.
It's just for an
This
instant.
creates a
By
temporary
coincidence,
dipole
the electrons might
called
be
an
in one spot more
instantaneous
than the
or
other.
temporary dipole, because it exists only for a very short period of time. In a collection of molecules, a momentary concentration of electrons at one end of a molecule repels the electrons in another adjacent molecule.
So it induces
In
the
this
other one
way,
to do the same
one
thing.
instantaneous dipole induces another dipole in a neighboring molecule. The dipoles attract each other by electrostatic forces, termed dispersion forces or London forces. Dispersion forces oscillate rapidly, being continuously turned on and off as the electrons continue their movement around the atomic centers. Because they appear only momentarily, they are rather weak on average. All the same, they are present in all molecules, regardless of their polarity. Dispersion forces are the major attracting forces in substances composed of molecules, especially nonpolar ones.
Okay, so again, all four types of intermolecular forces have to do with the positive end of one molecule is attracted to the negative end of the other molecule. Just the extent of that attraction is different based on whether it's a full positive and negative like ionic versus a partial positive and negative like polar versus an instantaneous partial positive and negative that happens on and off like in London dispersion. So when you look at a molecule, how do you know what type of intermolecular forces it has? Well, for the ones that I'm going to ask you what type, it's usually going to be a covalent substance, so we know it's not going to be ionic interactions. So once you figure out that it's covalent, what you want to ask yourself is the molecule polar? And if the answer is no, then the only type that you have is London dispersion. If the answer is yes, it is polar, then you do have London dispersion, but it's negligible because you probably have dipole or H bond. So then what would be your next question? Well, your next question would be, do you have an HF HN, or HO in your molecule? And if the answer is yes, then you have an H bond. If the answer is no, then it's dipole. So again, once you figure out if it's covalent, ask yourself, is it polar? If not, then it's London dispersion. If yes, does it have HF, HN, or HO? If yes, then it's H bond. If no, then it's dipole. So let's practice some of these and see if we can figure out if they are polar or non, and what type of intermolecular forces they have. So if you look at your packet on page 8, these are your Vesper notes that we started. So we're going to fill in the last column here of the type of intermolecular force. So first thing you ask yourself is this polar or not? Well, this one's nonpolar, so that means the only type that it has is London dispersion. Next one, this one we determined it's polar, so then you ask yourself, does it have HF, HN, or HO? It does not, so that means it is dipole. Next one, SH2, we determined that that's polar, so then you ask yourself, does it have HF, HN, or HO? The answer is no, so dipole. Next one, BeI2, we said that that was nonpolar, so that would be London dispersion. I'm going to use LD for London dispersion. BCl3, same thing, nonpolar, so London dispersion. GeBr2, we determined that's polar, so then we ask, does it have HF, HN, or HO? Answer is no, so that would be dipole. The next two are nonpolar, so since they're nonpolar, we're going to say London dispersion. HCN is polar, so then you ask, does it have HF, HN, or HO? The answer is no, even though you have an H and an N, but they're not bonded together. So that means it's not extremely polar, it's just regular polarity. So that would be dipole. And then the last one, nonpolar, so that would be London dispersion. Let's take a look at your worksheets. And let's do worksheet 4. How about that one? So let's look at this one here. So you ask yourself, is this polar? The answer is yes, it is polar. Does it have HF, HN, or HO? Nope, so it is dipole. Next one, let's do this one next. CH4, this is nonpolar, and so that would be London dispersion. Next one, this one is polar, and so you ask yourself, does it have HF, HN, or HO? So no, dipole. Next one, is this polar? No, it's not, so London dispersion. O2, is this polar? Nope, it's all symmetric, so London dispersion. Is this polar? Nope, it's symmetric. Top is the same as the bottom, side is the same as the other side, so nonpolar, and it will be London dispersion. Next one, SI2, that is polar, but it doesn't have an HF, HN, or HO, so dipole. This is nonpolar, so London dispersion. This is nonpolar, so also London dispersion. And this one is polar, that's the one we just did, but it doesn't have an HF, HN, or HO, so that is a dipole. How about, let's go to worksheet 3. Let's practice a little bit more. So we already determined the polarity of these in the previous video. So pH3, that is polar. Does it have HF, HN, or HO? Nope, so dipole. HBr is polar, but it doesn't have HF, HN, or HO, so dipole. N2, nonpolar, London dispersion. H2O is polar. It doesn't have an HO, it does, and so that would be H bond. Finally, we found an H bond. Next one, PF3, polar, but it doesn't have HF, HN, or HO, so dipole. For number 6, this is polar, but doesn't have HF, HN, or HO, so dipole. And then all of these we said were non-polar, so all of these are just London dispersion.